Hi everyone, my name is Greg, and in this video I'm going to be going over the ratio and root test and their uses. In addition, I'm going to be going over the use of power series, and I'll be showing a few examples of each. I'm going to start with chapter 10.5, which covers the root and ratio tests in detail. The purpose of these two tests is to help determine the outcome of an infinite series. If either of these tests have an outcome of less than 1, it can be said that the series converges absolutely. Because of the absolute convergence theorem, I should flash this on the screen here, we know that the series will then be defined as convergent. If for either of these tests the outcome is greater than 1, the series diverges. And what about 1, you may ask? Well, unfortunately, if it's 1, these tests are inconclusive and another test will have to be used to determine the outcome. Now that we have looked at the basic foundation of these and how they're used, it's time to get into a few problems to demonstrate how they work in practice. I'm also going to point out a few things of how to spot or just get a gut check of if these problems are going to actually work. Alright, so let's take a look at number 7 in the homework problem. So this is from my book. This is going to be using the ratio test. Something to note, which makes this problem very nice and a good example of a ratio test, is we have a fraction. So this is going to be something divided by another something. We have factorials in the top and bottom. This is a good use of those. We have an exponent that is being multiplied by a constant, which is a good thing to note, and we have a negative 1 out front here. So this negative 1 is going to be taken into account when we have absolute values, and the factorials are going to be taken into account because the ratio test is the limit as n goes to infinity of the absolute value of n plus 1 over n in short terms. So let's go ahead and write out this big ratio here. I'm going to go ahead and flip this over because this is going to be divided by n, so I'm going to multiply by the reciprocal. So we can go ahead and start canceling here. One thing to notice is negative 1 to the n and negative 1 to the n plus 1. These n's are going to cancel, which just leaves you with negative 1 to the 1, which is just negative 1. That's going to go away because of our absolute value bars on the outside, so we can just completely get rid of that. Our n plus 2 factorial and n plus 3 factorial. For those of you that don't know, we have n plus 3 factorial is the same thing as saying n plus 3 times n plus 2. That's a 3, oopsies. N plus 2 times n plus 1 times n dot 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 until it gets to nothing, or until n approaches the nth term. And then we have n plus 2 in the denominator. This is going to be divided by n plus 2 times n plus 1 times n dot dot dot. You can see how things start to cancel, so the n plus 2's go away, n plus 1's n's goes away, so on and so forth. All you're left with is n plus 3 in the numerator. So we're going to go ahead and delete this real quick. So I'm going to go ahead and cross out this factorial. I'm going to get rid of the n plus 2 factorial. And then our n plus 1, where is that paired to? I'm sorry. This should be a factorial, shouldn't it? Yep. There we go. N plus 1 factorial and n factorial. This is going to be the same thing, except for we're just going to be left with only the n plus 1. That goes away. Then we're going to have a 3 to the 2n and 3 to the 2n plus 2. I'm just going to go ahead and rewrite this out here just for a second. Let's go ahead and select this guy. I'm going to get rid of him. This is going to be 3 to the... Oh, my bad. 3 to the 2n plus 2. Then we have 3 to the 2n. That's going to cancel up here, which just leaves us with 3 squared. This whole thing goes away. So let's start simplifying. We're going to take the limit as n goes to infinity. We're going to have a n plus 1 squared. We can write this out actually. Let's go and do that. We're going to have an n squared plus 2n plus 1. And this is going to be multiplied by n plus 3. n plus 3. Absolute values, don't forget those. Divided by, everything else is canceled, and that was a bad line. Divided by n plus 1 times n squared times n squared, or sorry, times 3 squared times n squared. So this is really going to be, I'm just going to leave it n plus 1, and the 3 squared is 9 times n squared over here, just leaves us with 9n squared. Then we can go ahead and factor this out real quick. So we're going to have the limit as n goes to infinity. Our n squared becomes n cubed. N cubed plus 3n plus 2n squared is going to be plus 5n squared plus 1n plus 3 is going to be plus and the n's go to 3n plus 3. And this is going to be divided by 9n cubed plus 9n squared, absolute value. Now, if you go ahead and plug in n into infinity into n, you're going to be left with infinity cubed over infinity cubed, which is irrational. You can't really do that. So we're going to have to simplify this first. So we're going to divide the top and bottom by the largest nth term, which is going to be n cubed. So we're going to go ahead and write this over here. We're going to have n cubed over n cubed plus 5n squared over n cubed. Sorry, let me rewrite that one. Squared over n cubed plus 3n over n cubed plus 3 over n cubed, all divided by 9n cubed over n cubed plus 9n squared over n cubed. Now what you see is this cancels. That just leaves you with the number 1 plus 5n squared. This goes away, just leaves you with 5 over n. This once again just leaves us with 3 over n squared, and this is just 3 over n cubed. This leaves us with 9. This one goes away. That's supposed to be an n. My apologies. And then this is simplified version. Once again, this whole thing is absolute value and taking the limit, but I have run out of space clearly. So let's rewrite that. Now we can evaluate this. So this is all perfect, ready to evaluate. Plug in infinity. 5 over infinity is 0. This goes to 0. 3 over infinity squared, 0. 3 over infinity cubed, 0. 9 over infinity is 0, which leaves us with 1/9. And as we know before, the ratio test says that if n is less than 1, then therefore it converges absolutely. 1/9 is in fact less than 1, so we can say that this summation converges absolutely. And because of our absolute convergence test, we know that this then converges. Continuing on with the root test. This test uses some of the same principles of absolute convergence, but it's a bit more simple in terms of mathematical work. The basic requirement is to take the nth root, or 1 over n power, and in most cases this will cancel out another power of n, leaving with just the absolute value of an easier sequence. Alright, let's take a look at this problem here. This is problem number 10 in my workbook. This is the root test that we're going to be using here. A nice indicator for the root test is that all terms are raised to the power of n. That's just a dead giveaway that you should be using the root test. And you're going to want a difference in power. So sometimes if you have an even number of powers and they have the same, I say powers and I'm talking about the n right here. So if this was like just n and this was a 4n, you might run into problems there if your coefficient was the same, because then you could run into having equal 1. So that's always just something to be conscious of when you're doing these problems, but this problem works out in the end. Let's go ahead and use the root test on it. So to start out with, we're going to take the limit as n goes to infinity of the nth root. So we're going to do nth root of the absolute value of 4 to the n over 3n to the power of n. Now you can see a little cancellation going on. We're going to go ahead and take out the n of this problem here. There's no negatives, so I'm going to go ahead and bar the absolute value sign. We're going to continue on here though, so this is equivalent to limit as n goes to infinity. This is going to be nth root, and we're going to have parentheses 4 over 3n to the power of n. And once again, that absolute value sign, everything's positive, so I don't need to worry about that. The 1 over n multiplied by n simply gives us a power of 1. So this is going to go to limit as n goes to infinity of 4 over 3n. And this is where you can evaluate this nth root test, nth term test, by just plugging in infinity, which gives us 4 over 3 times n as n goes to infinity. We're going to call infinity, which is the same as 0. Or this is equivalent to 0, because 4 divided by an increasing large number multiplied by 3 is going to give you 0. This is our n value, so we're going to say, like we said earlier, n is less than 1, then we know that this is going to converge because it's the root test, and it's going to converge absolutely because of our absolute convergence theorem. So we know that this is going to converge absolutely because 0 is indeed less than 1. And because of this, we can say that this whole thing converges. Alright, we're going to take a look at number 62. This says, assume that the series a sub n x to the n converges for x equals 4 and diverges for x equals 7. So I'm going to go right ahead and put 2 points at x equals 4. This is centered at 0. 1, 2, 3, 4. And diverges for x equals 7. 5, 6, 7. Let's see. Answer true t and f and n for not enough information. All right. So let's go ahead and look over at theorem 18. So this theorem states that the absolute value of x is less than the absolute value of c. Then it converges absolutely within those. And vice versa, for the absolute value of x is greater than the absolute value of d, meaning that's going to diverge. So basically what we have here is anything beyond here is going to diverge. And if anything is less than the absolute value of 4 in our case, it's going to converge. And this goes to negative 4. So I'll do this in blue here. So we go 1, 2, 3, 4. So in between this range here, excluding 4 and negative 4 is going to converge. And red is going to be anything past 7. Let's get rid of that. Anything past 7. And in between we don't really know anything about. And of course that's at negative 7 as well. So I'll write a little line this way. Arrow, arrow, so on. You get the idea. Let's head back down here. So let's take a look at this. Converges absolutely for x equals negative 4. Now it tells us that we converge for 4, but we don't actually have any information on converging absolutely for x equals negative 4. Now it says it converges absolutely for the absolute value is less than c. So let's say c was just slightly less, then we could say it converges absolutely. But because we know that it's equal to 4, so in this case the absolute value of 4 is less than 4. Sorry, that's negative, because we're looking at negative 4. This is not true, because 4 is not less than 4. So we can say this is false. Same logic applies over here, but diverges for 5. This actually, unfortunately, falls in between 7 and 4 on our number line here. So we don't have enough information really to figure this out. I'm going to put n, a, or just n. Converges absolutely for x equals negative 8.5. Well, as you know, the absolute value, it does fall, so this is our negative 7 mark. And negative 8.5 lies beyond that, so this is going to be completely false. It's actually going to diverge there. I'm going to say false. Converges for x equals negative 2. On our number line, that's right over here, and it is going to converge absolutely. So we're going to actually, unfortunately, have to say that's false because it converges absolutely there. So we're going to say this is false. Diverges for x equals 8. This is true because it's just past 7 over there. So I'm just put a little t there. Diverges for x equals negative 6. That falls in between our negative 4 and negative 7. So we do not have enough information to really say about what that is. Converges absolutely for x equals 0. At x equals 0, it does indeed converge absolutely, so we're going to say true there. And converges absolutely for x equals negative 7.1. That's actually just outside of our range of divergent and well past our range of unknown. So we're going to have to say that is completely false because it's not in our negative 4 to 4. All right, let's take a look at number 63. So similar to 62, we have a power series, but this time we have a center shift. So we have an x minus 2. This one we have x and a negative 1, so we're going to put that right over there. And we have a 6, at x equals 6, so that's positive 6. And at negative 2, because of that center shift once again, our negative 1 then goes up to positive 5. I'll write that there. Sorry about, oh, that's the wrong color. Let's swap colors real quick. Positive 5, there we go. And then we have because of this, we can solve for a r value as well. Converges, all right, so then we're going to start out by solving for those r values, which I did up here, just to save on time. We have absolute value of x minus 2 is less than 1. So we're going to take positive and negative 1, and we're going to add 2 to both of those, which gives us 1 and 3. We have those plotted right here, as you can see, 1 and 3. And then we can start off here with converges absolutely for x equals 1. Now, this is an issue because of the, we can go ahead and plug in some numbers here, but we have sigma a sub n, and then we're going to do x equals 1, so 1 minus 2 to the power of n. And let's take a look at this. It says we converge for negative 1, but that doesn't really matter for this. 1 minus 2 is going to be negative 1 to the power of n, but we don't know what a sub n is. So with our with our alternating series test, we know that if the limit of n goes to infinity of b sub n equals 0, and b sub n is eventually non-increasing. Non-increasing is weird because it means that it can flatten out, but it can't go up. So it could be flat and then go down, and then flatten out and go down. So basically it has to do with the stair step or something close to it where it goes from point A to point B in a downward trend. So with that definition, we can't figure out if this a sub n negative 1 to the power of n is going to eventually become 0, or if it's decreasing or anything like that. So unfortunately, we have to say that we don't have enough information solely because we don't know what a sub n is. So for this one, I'm going to say n. Now we're looking at negative 6. So negative 6 is way, way, way down here. And I'm going to clearly say that diverges. It's outside of our reflected range for diverges at x equals 6. And it's outside of our convergence range. So I'm going to give that a big ol' true on that one. True. Diverges for x equals 2. That is right smack dab in the middle, and that's directly in the center of our convergence. So I would say that is 100% false, because at 2 this is equal to 0 to the power of n, which converges. Converges for x equals 0. This is in our secondary range of convergence. So this is also going to be true, because if it converges absolutely, it does converge. So this is true. Converges absolutely for x equals 5. So at 5 we have this weird point where we don't really know for certain if it converges or not, because all we know is at negative 1. So this is sort of problematic because it didn't tell us at 5 it converges, it told us at negative 1 it converges. So unfortunately we don't have enough information to really determine if that converges there. Diverges for 4.9, that's actually false because in that 4.9 range we're in that blue zone, so it's going to converge in there, so I'm going to give a big ol' F. Diverges for 5.1, once again not enough information is given because that's in kind of our weird, I'm gonna call it the rainbow zone. Yes, that's in our weird rainbow zone here where we don't know anything about the in-betwixt. So I'm going to say not enough information there. Converges absolutely for x equals 4. Let's take a look over at 4. Yep, that's going to be in our wonderful range of absolute convergence, so this one is also going to be true. Okay, so before we go on to numbers 21, 22, and 23, I want to preface it by talking about why we actually look at series and sequences. So series are a very useful tool of making a function into a polynomial. So we can use polynomial division, polynomial multiplication, and things like that because we've grown up with polynomials and algebra and things like that, so we know how to use them and manipulate them very well. This is very handy for figuring out algorithms and things like that, or basically showing something. My favorite personally is the ball drop experiment. So I shouldn't say an experiment, but basically you drop a ball and then the path it takes goes down, and then there might be a relationship between how high it bounces, but you could basically represent this path it takes with a series. You're basically continuously adding up all the distance it travels from where it starts to where it ends without having to say something like y equals, so on and so forth, the distance or the area of the derivative and so on and so forth. So it makes it really, really nice for making things like this really easy. And you use them later in life. That's the main thing I've learned from them, which is just very handy for me, and I personally enjoy those. Continuing on though, what do you know about rearranging the terms of an absolutely convergent series or of a conditionally convergent series. So over here I have a few listed out that I'm going to use in 22, but basically it's talking about multiplication of series or addition of series and things like that. So once you're in a series and you have something like the general form of, it's going to be sigma, let's draw a little sigma here, n equals 0 or n equals 1 to infinity. You have a sub n, and then you have your x to the n. And then you're multiplying it, oh, that's not an n. You're going to be multiplying this by the same thing, or multiplying by something of b sub n. But basically what I figured out, n equals 0, infinity, b sub n, x to the n. Basically what I figured out is you have to multiply each term of a sub n by b sub n, and each term of b sub n by a sub n. So basically what this is saying is if you had, for instance, a sub n over here, then you're going to have a sub n in the first term. So let's, I'm trying to think of a general case, but it's really not as easy as just saying a sub n times b sub n equals c sub n. This is not the case, and unfortunately it doesn't work. There's a little bit more to it, so you have to say a sub n at n equals 1 kind of thing times b sub n. And then that's going to be plus a sub n equals 2 times b sub n plus a sub n equals 3 plus b sub n, or times b sub n, and so on. So you get the idea. Basically, you have to multiply every single one of a sub n's by b sub n, and every single one of b sub n's. So it's like a very, very large, an extremely large, infinitely large foiling, if you will. So typically what you do with multiplication is you only list out the first few terms. Now addition, on the other hand, if this was a term you wanted to add, or sorry, this is still multiplied, let me get rid of that. But if you were to add these two, that's still multiply. There we go, adding these two, then you're just looking at a sub n plus b sub n. So these are simply going to add together, and you can live happily ever after. So this is equivalent. So this is correct right here. So this is really handy with addition, but multiplication is kind of a pain, so you got to watch out for that. Anyways, moving on. So I'm going to get rid of this stuff. Now we're going to look at the power series. What is a power series? How do you test a power series for convergence? And what are the possible outcomes? So power series basically come in the format of something to the power of n, and they can be multiplied by this a sub n term, which is basically changing each way it goes around. So the really classic one the book always gives is sigma n equals infinity, or sorry, n equals 0 to infinity, and if it's just x to the n, then you're looking at first term is going to be 1, and then you're going to add it to x, and then you're going to add it to x squared, and then to x cubed, so on and so forth. But basically this is this is a power series because it's the power that's constantly changing, and you're representing a function as you continue on. That's the dead giveaway, is it uses x's and you have powers involved in it, and you're going to be increasing exponentially rather than simply increasing a number each time. Let's see, power series. How do you test for power series for convergence? You can pretty much use any of the known series tests. A really popular one is to use a ratio test, because that helps with finding the radius of the problem, a radius of convergence, because that will set you up with an absolute value of something. Let's say it's going to be 16, and then you're going to, or 16 and then x is less than 1 is what you end up with if you use the ratio test kind of thing. Use something like the ratio test or the root test first to figure out what x can be equal to, or some other similar test before you can then just jump right into using one of those other tests, because you don't know what x is equal to. So you got to figure out within that bound of x, so like we had on those number lines earlier, from the lower bound of a to the upper bound of b, do you have a hole at a, do you have a hole at b, similar to up here in the graphs, and like what's in between, what's happening kind of thing. So you have to be able to watch out for those endpoints and the special cases and such. All right, continuing on. How do you test a power series? Oh, you're talking about what are the possible outcomes? Oh, look at that. These are the possible outcomes over here. Why is my, well, I have a graph now. So the possible outcomes are listed. So basically, if you have your interval of convergence from a minus r to a plus r, a is just your center. So it depends on if you have a center of 0 or if you have a center of something like a or something like 3 or b, anything like that. You basically add them or subtract the radius of your convergence. Once again, generally that's found with the ratio test. And that will get you a really good indicator of where those points are going to be. And then you have to test those points for convergence or divergence. So that's a pretty dead giveaway for those. And then it ranges from, if you have a radius of infinity, you're going to converge everywhere. And if you have a radius of 0, you're only going to converge at A and nowhere else, because obviously there's no room for these to go anywhere. And then these 4 cases are just variations of if you have a radius and then how much of that radius is actually either converging or how much of that radius is diverging. And when I say how much, I mean the endpoints. So either we have both of them, one of them, the other one, or neither of them converging. Those are the general forms that you'll see. So in 23, we kind of already talked about this earlier, but the basic facts about sums, differences, and products of power series. Basically with the sums and, the products, we run into that issue, and products and division are going to be kind of inverse of each other, but you got to really be careful about lining up a sub n and b sub n. You can't simply say that this is going to equal c sub n or ab sub n kind of thing. You got to really watch out for that and make sure you know that each term is going to have to add together. So realistically, if you're going to be multiplying 2 series, it's really tedious, and you're only going to want to list out maybe the first few if you're going to get an approximation. However, sums and differences, it's as easy as just combining the 2 of them. That's very handy that way. All right, let's talk about number 23b. So it's asking about substitution of a function for x in a power series. This is really straightforward, actually. As long as you have the same radius for x and f of x, you can sub it right into the sigma. So that's not a big issue at all, and this is actually really helpful for term-by-term differentiation and integration. I have this written down below. So if you have term-by-term differentiation, I say written down, I copied it. X minus a to the power of n. First derivative is just going to be chain rule, so you multiply down by that n, keep the c of n, and then of course the x minus a stays constant, and you have your n minus 1 on the top. So that's not really a big deal, and then it just shows the second derivative as well. You're going to multiply by that n minus 1, and I might have said chain rule, but it's really just power rule. It's just chain rule for the second part here, because you're kind of multiplying by the inside of it. And then you have your n minus 2. So it's really, really straightforward, and this basically differentiates all your terms. One really important thing to look out for is if you're not working with power rules, so let's say you have a trigonometric identity or trigonometric series is what I wanted to say, like sine of x over x, or sine of x over n or something like that with sigma. This doesn't work out the same way because this diverges in the long run, because it's going to keep going up and down and up and down and up and down and up and down. So you need to watch out for that and make sure not to confuse those two. Continuing on, we're going to look at term-by-term integration of the power series. It's pretty much the same thing except for integration. So if you have something like, we're going to do ncn x minus a, whoopsies, a to the n minus 1, and you want to integrate this. This is of course a sigma, n equals 0 to infinity. Then you're just going to take the integral, or antiderivative rather, of this whole part here, the c of n. It's going to hang out, and then you're going to be left with c of n x minus a, and you're going to add 1 to the power, so then you just have an n, which is very similar because that's the antiderivative of this function here.